not expect gassy tunnel conditions here. We also performed a wide array of laboratory tests for rock properties that influence both tunnel design, lining design, and tunnel construction. Additionally, bathymetry was performed in near-shore areas to confirm the amount of cover over the tunnel, the ground elevation. And we've done some additional studies and some future exploration. Disturbance, seismic refraction survey was performed at the south portal. Rock in more detail and get information about rippability, which is excavation using mechanical equipment rather than blasting to get a better understanding. Create ground disturbance in environmentally completion of necessary studies. Additional exploration at the shaft and portal locations to give them locations. So in this image, you see in the Upper Silurian, 470 million years ago. Claystone and water-soluble layer cake geology, nearly flat-lying sedimentary rocks that were operation of these shallow marine waters. Layers of shale and claystone in the groundwater level changes resulted in dissolution of nearly all the closed under the load of the overlying rock strata. And those overlying rock strata are what we now breccia is angular rock blocks and by secondary limestone deposition. Seen at outcrop locations on the St. and also Mackinac Island feature resisted erosion and the harsh climate. From the youngest to the oldest in the project area, we have soil and 3 rock formations that are the Bois Blanc, shown in green, Shem Formation, shown in pink. But the soils are much younger and were deposited during much later periods of glaciation, which ended only about 14,000 years ago. The weight of the retreating ice sheets was imposed over these glacial soils. Shallower, water-sorted glacial till, which is a mixture of gravel and sand and silt and clay, which make up a significant percentage of ice. Tunneling can handle most of this quite well. Cutter damage and cutter wear, groundwater pressure in soil. Look at some of the rock core obtained during the exploration. It's 2 5-foot-long core runs. The core diameter is 2.5 inches. Bit, and an inner barrel containing the core is then pulled up ship bottom of the lake. So to right, from top to bottom, the Bois Blanc and limestone. It's often sandy, and it has occasional to frequent minerals. So this is the rock of the TBM cutting tools. Cream and light buff colored Blanc from an engineering And then below that is the Pointe aux Chênes on the right. And irregular pockets and less abrasive rock. And it can be therefore be tunnel tooling, so there would be fewer. However, the claystone is prone of the rock in the presence of air and water. The images that were shared earlier in the presentation, the cutter. There can also be problems with clogging due to pipe that carries the excavated material out of the and it can have squeezing behavior at depth. Shield or the can of the TBM as it's advancing. So squeezing and clogging are managed with TBM features and tunneling means of practice TBM and have been considered in design and constructability planning. So the breccia is fractured and permeable, and as Mike Mooney explained in his introductory materials, which is equivalent to 570 feet of water at the deepest point. Local preferences whether cutter changes can be performed at atmospheric pressure, or whether it's necessary to use special methods, which John Hurt will describe in more detail later. Shaped the design approach. They influenced the design of the tunnel lining. Some of these risks are very low. Steep, buried valley, such as methane in the bedrock. We don't expect these conditions based on the They can be managed with some adaptations that are feasible during conditions within the breccia are known to be variable to the rock conditions, which include zones of problem during advance of the pressurized phase TBM, as John will describe. And that is addressed with the injection of a clay-based material to limit the squeezing potential around the those risks of clogging. That's managed through TBM features at the cutter head and also managed by slurry discharge pipe to limit the risk of clogging in the slurry discharge line. Other data from the rock testing, such as abrasivity and hardness of the rock and its strength, contribute largely to estimates of tunneling progress rates and cutter wear, which are important to estimates of cost and schedule. There is an additional broader consideration of having enough data to characterize the rock conditions along the alignment. The borings for this project are a portion of the channel. That's to increase our level of confidence in defining the top of rock elevation in this reach. We developed a serve as a basis for specifications for state-of-the-practice TBM technology and tunneling means and methods. While more data is always helpful to provide a better statistical estimates of cost and schedule, we do not anticipate that additional and tunnel construction methods. As John will describe in more detail, the TBM specifications require a pressurized face machine, so mining occurs. The TBM be equipped with multiple features that facilitate safe cutter changes and other maintenance. Holes, probe holes, ahead of the face, and that the TBM be capable of grouting ahead of the face. So the tunnel design and construction considerations were driven by the ground conditions. And after the next step was a qualifications-based procurement process through which Arup was selected as design engineer of record. Independent design review at every milestone submittal. The technical requirements for design services include specific design criteria and design review. We followed a full consultation with Arup engineer. We concur that the tunnel is constructible, the geologic setting and the subsurface John will describe in the next section. We have also, and we concur that the tunnel constructed in accordance with the plans and service-like requirements, which are maintenance service as vital infrastructure. On to describe the tunnel design.
The tunnel boring machine itself will useful to use that noise to look ahead of the boring machine?
Arup technologies and has taken into consideration the possibility of using those methods, and the tunneling contractor has the opportunity or the option to implement those methods at their discretion. In addition to the more low-tech means of the specifications as being
added to that?
With the repeat, please.
These are chemical.
Slurry is bentonite, which is a naturally occurring clay mineral, and there are some which are environmentally benign.
Okay.
Mr. Novak or Mr. Nystrom, question?
Analysis had been the presence of hydrogen sulfide, the characteristics of the of the borings. Can you go into a little more detail as to what the characteristics of the groundwater were in those locations?
We had no whatsoever. We had levels just above the detection limits for methane, so very low. In regions in Metro Detroit, where there are gas problems and tunneling, the methane levels are multiple orders of magnitude at this site.
Hydrogen sulfide. Were there other characteristics of the ground?
Basic groundwater chemistry, some chlorides, sulfates, those were of some importance for concrete durability, which Arup conducted.
How about the presence of brine?
evident in the that would have been indicative of brine.
Okay.
One,
The groundwater was very similar in its chemistry to the lake water, with slightly higher but not drastic.
question, is radon ever a problem?
Radon, Lisa.
We didn't do any testing for radon, but it's not typically.
Your subsurface profile and presented the different in the substrata. If you superimpose the projected depth of those different substrata, would the projected tunnel?
Primarily in the Pointe-aux-Chênes and of the selection of the imposed image, so you will see that.
That question for sure, because see the current design alignment and where drawing with that alignment.
Great. Was projected, or I think actually it was Mike Mooney who projected that the depth of the tunnel would be 560 feet. What is the in terms of its depth?
Question is when you consider the existing tunnel alignment design, at what point because I know we could answer a question too about how much bedrock we have over top of. Lisa, would you mind, or do we want that question for John?
To address that.
That'll work.
But there is the tunnel at even its shallowest point, and for the most.
And I will make sure.
I think it'd be good to come back to that when the profile image is up.
I'd like to go in the drilling. You said that if there were more boulders, there would be more. What? And then
in the selection of the alignment. Boulders are only present in the glacial till.
I see.
Question. TBM itself is that
100%.
Okay.
We're gonna dig in deep on the TBM.
Okay.
Move on.
At the end the questions for Lisa. Thank you, Lisa.
The only other question I have, getting back to the characteristics of the groundwater that were sampled, have those sampling results been shared with the authority or with staff?
Absolutely. Those are in the geotechnical data report, the GDR, which has been published and is available.
Thank you.
Right. All right, Mike Mooney, I'm going to move us on then. Thank you, Lisa. Over to you.
Good morning, everybody. And as mentioned in the next series of slides, I'm going to be describing the design process that we went through at the start of the design phase of the project. And primarily what we were looking at here was to select the tunnel construction approach, the alignment, and the diameter.
John,
Just a reminder.
John, before you move on, can I just get you to turn your camera on so we can see your face?
I think it's on.
Oh.
Is it not coming up?
Is it, to our tech team, is it not coming up?
Yeah, we can see you, John, on the Teams call.
Okay. We can't see you in the room, but if they can see you on the Teams call. Sorry, John, please carry on, talking about the alignment and tunnels. Yeah.
No problem. Yeah, just a reminder, my role on the project is I'm the subsurface design lead, which means I'm responsible for the design of the tunnel and the portal structures as part of the Arup team. So in terms of the overall design, step one in the process is understanding the ground, which Lisa's already described in detail, but when the Arup team was selected, we took a detailed review of the factual information provided from the geotechnical investigation, and our geologists and engineers carefully reviewed all that information. We inspected some of the exposures of the rock that you can see in the local area. We reviewed the geological history and then produced a robust evaluation of the geological conditions along the alignment corridor. And with this information, the first decision the team made was the tunnel construction approach. And this built on the earlier option study that we heard about and confirmed the tunnel constructed by a tunnel boring machine was appropriate. And to give some context, there's currently hundreds of TBMs working around the world, and they have various diameters and arrangements. So our first job was to pick the one type specific that would suit this project. So this slide shows the layout of a typical tunnel boring machine, and Mike Mooney has already showed you some information on this, but just to ahead. Is then removed. You have a and various other bits not shown on lining is built in detail. Trees as Mike's already mentioned, one way we like the TBMs deep in the ground at pressure, which allows the labor to work as normal. And this red disc kind of shows the cutoff between the section of the TBM, which is at a pressure to match the pressure in the that will be bearing on the outside there. So all work inside the TBM and the vast majority of the work in tunneling happens. This TBM is designed to work in what we call pressurized mode, and that's where the outside pressure is high or closed mode. Some other projects where the ground is less permeable or there's less water around, both atmospheric. But one early choice we had to make on this project and this was a fairly operation being required. It should be noted this wasn't unexpected. I think this is the predominant approach method around the world. Alignments, there's one other important making process, and that relates to maintenance. To be carried out as you would normally. If you need to do work outside of where that red bulkhead was shown, then we need to be working under pressure. Call this in the industry, we call this an intervention. The main reason you would need an intervention is to replace over distance. They may wear down. So sending workers into the pressurized zone is the discussion. It's quite an important part of the decision-making process. If we can stop importantly, less permeable rock where the water won't flow through as quickly, then we can do what we call a free air intervention, which is you reduce the pressure on the outside of the machine to atmospheric, and the workers can go in under atmospheric pressure. If this isn't possible, then we know what we call are in a zone of higher pressure, and selecting between those two types is something there's details in the project specifications. The contractor will ultimately be responsible for determining where the TBM intervention locations are, how many there need to be, and what exact requirements will be the means and methods of getting in. Interventions, it's a bit like maintenance on your car. You have a whole series of planned maintenance. Every certain distance, you change out components just to stop them wearing past their usable limit. And then occasionally you have unplanned maintenance where something isn't working as planned and you need to stop, you need to go in and do an intervention. So those unplanned ones are harder to select a location for, and you need to be prepared for every eventuality, which we are with this type of tunnel boring machine. Most important factor of selecting the vertical alignment for the tunnel on the so the ground in the tunnel impacts the amount of wear on the cutter head tools. So selecting an alignment in less abrasive ground results in less wear on the tools and then secondly, pressure, if any, is with less permeable ground. So for selecting the vertical alignment, and when I say we, this is the whole project team. As mentioned before, we had the JD ability advice, and we had the design team and various advisors. Performed a rigorous comparative evaluation between them. And this image, and at the top of the screen is a kind of true scale in that the ratio between depth and length is as in real life. The scale is 10 times larger, so although it looks a really steep slope, but the comparisons between during operation of the TBM and also during interventions stopped, and also those key criteria and a number of other ones as well. Looking at these three alignments, they all have similar start and end points. And we've set them to be as shallow as possible. On the north end, where the rock is slightly deeper, and we have that. Sure, the so all of these question of feasibility. It's just risk, and the less it is. So it's is the one that meets your criteria the best. That's pulled out fairly early compared with the red and orange alignments. The ground is more abrasive and it's more permeable. The scenario out under pressure, so it's it was worse. And the red and orange alignments follow a similar path into the Point aux Chênes formation. Although not all the borings extend down, by that is that we need to know where the top of the Point aux Chênes formation is, and that's what the borings told us. We know that formation. So the only variation, red alignment maintains the same elevation and goes underneath it. And again, in terms of the risk evaluation, it being slightly lower risk, and the main reason for there is potential for boulders to be sitting in that overburden. There's potential of an unplanned intervention in that material that drove us to the so just a summary of the selected alignment, which was the orange one. We would look at the south portal, which is on the right hand side of this slide, which is equivalent to about the steepest highway grade. Go down to the Point aux Chênes, we stay in that strata with a minimum St. Ignace. When we get to the valley section, and then head up to the north. Moving on to the horizontal alignment, this was a much simpler choice. There's essentially a series of constraints around and the locations of the existing pipeline and the boring. Shaft, pipeline. Once we made sure elements and design decisions here related to the locations and the general approach to construction overall, including the shaft structures. So in terms of the TBM diameter, that is with the whole team, and we included here the TBM. We look from the inside out. So what do you need in terms pipeline. You have various utilities that allows you to access the tunnel. That gave us one diameter. Then we didn't want to go and get access to the cutter head. So available on these diameter was selected, and that although only by a few inches, we ended up with an 20 foot and 10 inches. Moving in the video, the TBM space for the construction phase as well as the permanent, and 400 feet long Straits, and we've located this box at the south side of the Enbridge property to allow the tunnel to dive down under the lake with enough cover. It needs to be 100 feet by 50 feet, so we'll build that access in the north end of the shaft, or the top right on this image, and the rest. The technical information at this location tells us this is nearly all in rock, just a few feet. Will be too hard to be removed just by mechanical excavators, so we will need to use controlled blasting to fracture that. Side, the North Straits shaft, the work on this side is much more limited. There's a shaft there to receive the TBM. And then we designed this to be 70 feet in diameter, and a single piece. In the south, one is the groundwater level, and the other is there's a much greater depth of overburden materials, about 40 feet. Watertight structural shaft lining that's the depth of the shaft, as mentioned before, was set so that the tunnel could remain in rock. We have about one cover, so another the overburden material. Once again, the rock itself will need some that to be removed. Once permanent tunnel access, those in more detail later on. Any questions on the overall design approach?
Just for the folks in the room too, that we're in right now, think about that portal for long room, and you kind of think about how wide will that portal be. Well, 400 feet long by about this wide, so it's a helpful. John, before we take new questions, I just want to circle back to some of the old questions that I think are relevant to this section. Mr. Nowak, you had asked about the depth of cover. And go back, I guess, to that image. As best you can to the depth.
Generally, there's several hundred feet of rock and overburden, and this is pretty dense overburden materials, as Lisa explained, due to the glaciation. On the shallowest location, and this is due to the fact we're diving down from the portal. And we've made sure we have at least one diameter. The top of the rock formation, and there's some overburden materials on top of that, and that's to make sure we have enough ground around the tunnel. Although
I heard the answer that you gave.
Okay.
Yeah.
All right, sounds good. So new questions to the board.
I'm just curious, have there ever been a sufficiently drastic failure that the tunnel was abandoned?
John, the question is, in your experience, has there ever been a situation so drastic where the tunnel boring machine had to be abandoned in place?
I can't immediately think of one. There's been instances where there's been breakdowns or stoppages for other reasons for a few months while repairs have been taken on. But I can't think of one where the project has actually had to just stopped and been abandoned.
Yeah.
Using this type of TBM technology, there was an instance in Detroit, but it was not a pressurized space.
I mean, one of the
Correct.
reasons for
Yeah.
stopping might be that the cost had just become prohibitive. So it wasn't so much technically that you had to stop. It was more a question of whether the cost had just driven the tunnel beyond feasibility.
Awesome. So the question to our experts there is that, has there ever been a situation where a tunnel boring machine maybe was abandoned because the costs escalated to such a point where it couldn't proceed? Mr. England, did I get the question adequate?
Yes.
Okay, yeah. Lisa, John?
Not that I can think of. No.
Lisa?
No?
I can think of some projects where construction was delayed, but not one where construction was halted after it commenced without completion due to cost alone.
Okay, thank you. What about the habitability of the tunnel behind the TBM? I mean, you may have a couple of miles of tunnel there. People have to go through it. How do you keep it habitable?
So, guys, if you understood the question, John, was like, as the tunnel is advancing, let's say you're 2 miles in to the tunnel construction, keeping in mind the TBM is 500 feet, how do you keep it habitable? How do you keep it so that people can keep, because logistics coming in and out, one way in, one way out, what is the state of what's happening behind the TBM as it's progressing?
Sure. So in terms of making it a suitable environment, that's primarily ventilation. So as the tunnel is constructed, the contractor will hang a duct in the ceiling of the tunnel, and they'll blow in fresh air into that, and then so that fresh air will come out at the TBM, which is where nearly all the workforce is, and then that fresh air will supply that area, and then it will feed back through the tunnel and vent out through the tunnel. Typically, the only work in the tunnel itself between the TBM and the surface is bringing in the supplies, and they use these tunnel service vehicles, which are kind of large, large all-terrain vehicles that will kind of bring the segments into place and any other equipment needed ride in and out on one of those vehicles.
Okay.
But yeah, it's primarily a ventilation system, and I do standard in the industry like gas testing and things like that to monitor that whole situation.
Just at the end of the tunnel, why not just over TBM down there? Wouldn't you need you wouldn't need as big a shaft, would you?
I mean, that's certainly something we looked at. I think we would still need a shaft that would be fairly similar in size. When Aaron goes through the layout of that shaft, you'll see that it's fairly full of to save a small amount on the shaft, but not enough to make it economic to abandon the TBM. But it's certainly an option, and on projects where maybe there's certain factors which are driving you to do that. That has.
Just a question. Than you were saying they were. Well, that place on the south side is somebody going to address that and what that'll do to the environment?
Lisa, I'm going to throw a question back to you. Mr. England's question to you is, silt and we separate and pull out material that's left that will be removed from the site. How do we make or leaching? And he had a really great example. We know those Mackinac winds can be powerful. So how do we prevent around the site? Can you comment on that, Lisa?
Sure. So dust control is commonly accomplished with misters, and dust control will be the responsibility of the facility that accepts that material. The bentonite that will be within the excavated material that was used for the slurry, because it's not, some of it adheres to the excavated, broken up rock and sand-sized particles. That would be mobile on a dry, dusty, windy day. And so until the disposal area has been fully capped and vegetated, are typical on construction sites or other fill sites, just like highway fills. That will be
advantage we have over a highway site is this is a very repetitive. The where the material comes out, so they can set up their
enclosures planned on the disposal site, but on site undescribed.
Got it.
Animation.
Great. Mr. England, did you have a follow-up?
I had have there been problems in the past disturbing neighbors, a bad citizen while that's going on?
Excellent question, because maybe Lisa answering this one, or the north side, and we have to use some of the blasting methodology. What were noise and or movement any of the neighbors?
There are specification limits on peak particle velocity measured at the ground line of adjacent structures. At the distances that we are to other facilities, to other buildings and neighbors, this is a very easy project to manage blast vibration impacts. We would not expect that the from off-site. And uses the amount of ground vibration that's transmitted.
Just jumping in here, before we more questions from the board members here, we can transition to tunnel lining design, but let me ask one question. Showed the preferred alignment all in bedrock. Could you comment, you made a comment about is, so the point of Shane, for example, the rock conditions below the existing borings will stay consistent. That's part A. And then part B is if construction method been designed to capture that. If you could just summarize those two pieces, I think that'd be helpful.
Yeah, I think the first one in terms of the consistency is really, we have a geologic understanding of how this formation, and then we have these data points. You'll see there is a number of D on the north side, on the left-hand side of the screen. To validate our understanding of the formation. In terms of the second part, we all, on the theme of risk, we're always prepared. And this, this type of tunnel boring machine can essentially, because it's kind of designed for the worst case scenarios. So ground, and we can use the pressure ahead of the face to support that ground. The kind of excavation, which I'll talk about in a slurry, can handle a wide range of possibilities. There may be more wear, so you need more interventions. You may go slower than we currently planned, but in terms of what the machine can handle, reliable road vehicle, they're designed for higher speeds, and we actually use them for in.
All right, thanks, John. We had tunnel line.
Yeah.
Oh, sorry. Go ahead.
Mike Mooney, just wait. We do have a follow-up. We have a couple. Let's take this question.
Just a couple questions. The first one I think is pretty easy. On the horizontal alignment that was presented, you indicated that part of the the boring locations that had been performed earlier. I was wondering, what was the minimum distance between the envisioned horizontal alignment and the boring?
We have 25 feet was our criteria for that.
All right. And then second, can you give me a more detailed description of what you mean by unplanned interventions that you have encountered on past projects?
Sure. Assess all the ground conditions based on the information we provide them with. intervention, they'll change out a number of cutting tools. You know, they have call rates of wear of these cutting tools based on the ground. So they'll make this. It may not be every 500 feet because they may look at the stretch where the and they can pressures being used, so that may sometimes can break. Boulders or anything like that, but if something, the metal coming through the slurry system, an unplanned intervention, that's certainly one I've come across on projects. The other one, which is rare but does happen, is that the actual cutter head itself, if something that needs to be repaired, then that, and you probably get
under
yeah, can't remember the exact numbers, but that's been used in the schedules.
For people to so it's a so we were thinking on average less by any stretch. It's advancing, putting up a ring. And
yeah, often.
Yeah.
So
oh.
10.
John, do you have need to change the cutter tools? Like, what? Do you recall the estimates on what we're kind of thinking for in that regard?
I'm stretching my memory here, but I think somewhere between 500 and 1,000 feet, and maybe others can remind me. I know we did. It wasn't consistent along the tunnel because in that first section, when you're going through the Bois Blanc and the Saint Ignace formations, the machine will be brand new going into those. So I think we had fewer interventions than we had them on a more regular basis. And then the frequency, because they're slightly more difficult interventions. And of course, this is just our preliminary planning when the approach, and I know some contractors like to do more preventive maintenance. You know, others have a different balance. Your car, if you have a 5,000 mile service, some people will say, well, I'll may take it in months. So
like as breach is a little different. So based on using the tool, all the information that's been, and then make that plan and then execute.
And I want to let everyone know that I know there's and the video of this meeting will, you know.
All right, Mike Mooney. I'm moving. I'm going to give him a chance to take a quick bite of water. Made when we signed the tunnel agreement. So we said we're going to line this with concrete. Now that the design has progressed to where it is and we're virtually done that design, concrete segments are going to be about 15 inches thick, and we're going to have 2 rows of gasket seals. The decision on the tunnel lining was actually, that was one of the big lifts with the joint specifications. That joint specifications team was made up of representatives from the Michigan Department of Transportation. This group had representatives as well as Arup, as well as WSP, and as well as Enbridge. So that developed specifications that define the technical requirements of the tunnel, including very specific lining. It's not just the design of the lining. Those specifications also, we want them manufactured well in an environment where we can guarantee the quality. We also have to design this beautiful transported. So there's details that it's not so simple as just what's the design. There's more. I'd love to talk about liners. So let me
talk about these for a long time, but yeah, so we're forming the tunnel lining as was described earlier with precast concrete segments, and these are assembled together to form the lining. Now, just like TBMs, this is a well-established technology with hundreds of miles of this type of lining being built each year. On this slide, you can kind of see on the left the typical components of the rings, and each ring is made up of a number of pieces, and the key you can see labeled there is like a wedge-shaped piece that goes in last to form the lining. On the right, you can see a typical tunnel.
John, just as it's being constructed, that's a tunnel in construction, right?
It is in construction. Ours would be slightly different because we have a slurry TBM. There'd also be some pipes on the side that allow the slurry to be pumped in and out. And because of the gradients we have, we would be using rubber tire-based equipment, so you wouldn't see the rails.
You won't see the
rails. But in terms of generally this tunnel,
the environment
is how it would look. Yeah. That we've developed for the Great Lakes Tunnel Project. So in our case, each ring of segments is 6 feet in length, and comprises of 5 large pieces and 1 smaller key. The segments are 15 inches thick, strength reinforced concrete, plus some steel fibers to provide some additional ductility. The segment we manufacture, so this allows for to talk a little bit. Our design included several aspects. Firstly was the structural analysis, so side of the tunnel, and also all the loads during manufacturing and construction to make sure that the the lining is strong and robust and can deal with all those lines. So we, our materials engineers, this is what they do in life, which is 99 years in this case. Humidity, maybe sulfates and chlorides in the groundwater. Define the concrete mix requirements to make sure we meet that design life. Then we also design for extreme events, the likelihood of happening, but we still need to design for them. And the key one here is a fire. So our fire engineers would look at different potential fire scenarios, and that allows them to define a maximum temperature for the fire and how that impacts any loss of strength in the lining as a result of the fire, so we can check the lining that remains still has enough capacity. It is a critical load case, and so it's going to be confirmed by testing. We will actually confirm its performance. The water ingress rate into the tunnel. So there's a very low water ingress rate specified as part of the design and construction requirements over the entire length of a tunnel location. So this may actually sound like maybe just one way of thinking about it is the equivalent flow is a garden hose. That's about 5 gallons per minute or so, and that rounds up to 7,000 gallons per day. Surface area is equivalent to 21 garden hose on 23 football fields. It gives you some idea of how dry the fairly typical for transport or utility tunnels. We recognize you don't get of water inflow. That's in the tunnel from condensation or maintenance operations will be collected in a tunnel sump on the alignment and then pumped out of the tunnel, and Aaron will speak to that in more detail. Roadway above the low point, allowing the water to collect in. The water tightness in a aspects. One is the segments themselves, so they prevent any water for very low permeability concrete, so they'll be essentially dry. Have rubber gaskets in them, so the rubber is like the rubber gasket around the outside of the windshield. And when the segments are assembled and pushed tight together, these rubber gaskets are also compressed tight against each other so that they mate up and they provide a tight seal. For degradation over the design life. And typically we require 200% of the required capacity at design life. They will relax to some extent and end up with about 140% of capacity. So still more than enough factor of safety above the water pressures, but it does account for the design life. Project, while the main purpose of the gas, there is a secondary purpose, and this is for the unlikely event of a release of hydrogen, or will act as a secondary containment system. And so the gaskets need to be part of that. We've specified gaskets with additional requirements for that reason. Lastly, on segments, mitigation, although we designed measures in place if there is any damage to the segments. Typically, if any cracking or edge chipping occurs after installation, we have some repair methods. Have been as the lining itself.
Mooney,
So
do we, yeah. I think we're good here in this room, so do we want to do a...
We're pretty good on schedule here, so if there's no questions from the board members, why don't we take a 10-minute break till the top of the hour and start up again.
10 minutes it is. We'll start up again at the top of the hour.